Today we're going to take a look at the Chapter 1 review. So we're going to review lessons 1, 2, 3. We skipped lesson 4, 5, 6, and then we skipped lesson 7. So we're going to skip lessons 4 and 7 throughout this review, and that material will not be on the test. So I'm going to do my best to do this without having to stop or pause or create multiple videos, but we'll see if that happens. So topic 1 review, there's a little vocab review up at the top. You're more than welcome to check out the key, right? That solutions manual that I put in Canvas to kind of see what those answers are. It's a great idea to understand what vocab words you're supposed to know, because questions on the test might say something like find the maximum, and then you're like, well, what's the maximum? So make sure all those vocab words, you got a solid understanding of what they mean and what they're expecting you to do if they use those words. So for lesson 1.1, this is all about key features of functions. If I remember right, there are, I think, 6. Domain, range. So domain is the width of the function. Range is the height of the function. Then they talked about if a function was positive or negative. So like in this example right here, this function is positive when x is less than 1. Because as soon as you hit x equals 1 right there and you go less than, notice that that function is above the x-axis. So that's all my y values are positive. And then when x is greater than 1, that's when it's negative because it's below the x-axis. So when they're saying positive and negative, they're talking the y values are positive. The y values are negative. Then they said increasing and decreasing. So increasing is basically going uphill. So like with this example here, between x equals -3 and x equals 2, that function is increasing. It's going uphill. Between x equals -5 and x equals -3, it's going downhill. So they say that that's decreasing. Another thing I think they talked about were x and y intercepts, and they literally sound exactly like what they sound like. X intercepts is wherever your function crosses the x-axis. Typically, it's referred to, like in this example here with number 7, my x-intercepts are x equals 1 and x equals 3. You could also say that the x-intercepts are 1, 0 and 3, 0, just a different way of annotating it. And then the y-intercept is just wherever your function crosses the y-axis. So with number 7, you could see it crosses the y-axis at -1. So again, same thing with the x-intercepts. I can refer to this y-intercept as y equals -1 or 0, -1 as a point. I think other than that, that's pretty much the highlights of what they were talking about in this section. So let's just kind of quickly look through this quick review, the example and the practice problems. Domain of the function is a set of all input values or x values. The range is the set of all output values or y values. So another way I like to think about it is with number 7. Let's take a look at this one. The domain is basically how wide your function can get. So if I look at number 7, it looks like right there, that's where it stops, right? It stops at -5. It doesn't get any wider than that. If I can actually put something there, right? It doesn't go any further left than -5. But if you look at the right side of the function, it goes down and to the right forever. It'll never stop going down and to the right. So I can't put a cap on this side. I can't say, oh, it's only that wide. No, that function goes right forever. So it's going to go off to positive infinity. So domain is the width of the function. Range is the height of the function. So if I look, it looks like that function only gets about that tall, and it goes down about that far. So that's how tall it is. It looks like it starts off at -4 and it goes up to +1. So that's the height. That's the range of the function. These sets can be described using interval notation or set builder notation. Interval notation's way easier, way quicker. That's the one where they have just like a something like this, right? Just a set of parentheses or a set of brackets. Let's see if we can find one with brackets. I don't see one on the page. But set builder notation, if you forgot what that looks like, go back to lesson 1.1, or interval notation, if you forgot what that looks like, go back to lesson 1.1 and check it out. It's basically, it almost looks like a point, except for it can use parentheses and or brackets. It just kind of depends. Set builder notation was a little more involved. That's the one with the curly brackets. You know, X is a real number such that kind of was a little more elaborate. But make sure you know what each one of those are. Look back in lesson 1.1 if you forgot. A y-intercept is a point on the graph of the function where x equals 0. So for example, in this example, x equals 0 means I'm not going left or right at all. I'm looking at going up to 2. So that's my y-intercept when x equals 0. And then vice versa, an x-intercept is when y equals 0. So if I want to find any of my x-intercepts, I can either just look at the graph. It's obviously positive 1, right? X equals 1. Or I can plug in y equals 0. So y equals 0 is that flat horizontal line right there. Wherever I hit my function, that's going to be my x-intercept, which looks like it's at x equals 1. An x-intercept may also be a 0 of a function. So there's lots of words for x-intercepts. You can say like, there's an x-intercept right there, right? At x equals 2. They'll call those roots, like roots of a tree. They'll call that a root of the function. They'll call them zeros. They'll call them x-intercepts. There's lots of kind of vocab words that they might use, almost like slang, to talk about an x-intercept. But zeros, roots, x-intercepts, I think those are pretty much the most common ones. An example, find the zeros. So here's zeros. So that's talking about the x-intercepts of the function. So it's right there. Then determine over what domain the function is positive or negative. So there is my x-intercept. That's where it crosses the x-axis. So that's going to be x equals positive 1. And then over when the domain is positive versus negative. So remember what that is. That's talking about when the y values are positive, when the y values are negative. So basically from the x-axis up, those values are all positive. From the x values down, those values are all negative. And if you look at our function here, it looks like from that point left, right? From x equals 1 left or less than, that function is all positive. It's all above the x-axis. So if I wanted to identify the positive part of that function, I would say all my x values that are less than 1. All my x values that are less than 1. And then for the negative part, I can flip that. You can see that function after it hits the x-axis, that's when it becomes negative. So that's all my x values that are greater than 1. They're using interval notation down here. The function is positive on the interval negative infinity to 1. So all that's saying is if you go all the way over to negative infinity to the left, all the way from negative infinity, all the way up to x equals 1, that function is positive. And then it's negative on the interval from 1 all the way over to positive infinity. Practice and problem solving. Identify the domain and range of the function in the interval notation. Find the zeros of the function, then determine for which values of x the function is positive and for which it's negative. So lots of stuff here that's happening. All right, so let's start off with domain and range. The domain is basically the width of the function. So if you're looking at this, it looks like the smallest x value that I'm dealing with, domain always deals with x's, range always deals with y's. So it looks like the smallest x value I'm dealing with is x equals negative 5. So it's right there. So problem 7. Let's see if I can do a better job at putting this on camera. Yeah, that's going to work. So domain, the smallest x value it hits is -5. And if you notice, that's an open circle. So for domain, it's going to be a parenthesis at -5, because again, it's an open circle. You don't want to include that point. And then all the way to the right, again, this function goes down and to the right forever. So it's going to shoot off to positive infinity. Then we'll talk about range. Range is talking about your y values, the height of your function. So it looks like the bottom part of my function, the lowest it goes, looks like it's right there at -4, but I think I might have misspoke earlier because I wasn't looking at this arrow over here. So this part, the lowest it goes is -4, but if you take into account this right side, remember this goes down and to the right forever. It never, ever, ever stops going down and to the right. So this is going to shoot off to -infinity because down is -infinity. But then up, if you keep going up, 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 it looks like it caps out right there, right? That's the tallest my function can get. So that's at x equals 1. And since you're actually hitting the function there, you're actually touching it, that's going to be a bracket. You can't actually touch -infinity and positive infinity. Those will always be parentheses because you can never reach that. It's not an actual number. It's just an idea. But since I can actually touch y equals 1 right there, that's going to be a bracket. Domain and range in interval notation, find the zeros of the function. So the zeros, that's my x-intercepts. Just by looking at that, it looks like it's x equals 1 and x equals 3. So my zeros, x equals 1 and 3. Then determine which values of the x function is positive and for which it's negative. So if you look at our function, it only exists above the x-axis between 1 and 3. So between 1 and 3, that function is positive. It's above the x-axis. So I'm going to say positive. It exists between 1 and 3. Why am I not using brackets? Well, because I don't want to include 1 and 3. At x equals 1, that y value is 0. 0 isn't positive or negative. So I don't want to include 1. I don't want to include 3. I just want to say every point between 1 and 3, that function is positive. The y values are positive. And then negative, it looks like it's negative from -5 all the way up to 1. So from -5 to 1, right? From -5 to 1, that's all below the x-axis. And then same thing from 3 on. This goes down and to the right forever. So from 3 off until infinity, it's negative. So I would say from 3 until infinity, it's negative. Number 8, very similar problem, just a different function. So I'm just going to kind of try to save space here, see if I can use the same kind of information so I don't have to rewrite all this out. So my domain, the width of this function looks like it runs from -5. And again, this goes down, up, and then it goes to the right forever. So I think my domain is going to be exactly the same, -5 to infinity. The range is the overall height of the function. Okay. So it looks like it's going all the way down to -4, and then it's coming up, but it's flatlining at y equals 1. It looks like it's going straight to the right forever at y equals 1. So in this case, the range is just from -4 to 1. So from -4 to 1. Again, I want to use brackets, not parentheses, because you actually touch that function at -4. You actually touch that function at 1. Okay. So domain range, my zeros, looks like there's only one at x equals 2. My positive part of this function looks like from the beginning all the way up until x equals 2, it's all negative. The y values are all below the x-axis. But once I pass x equals 2, then it's positive. It stays above the x-axis. So the positive version is going to be from 2 to infinity. And then the negative version looks like it's running from negative 5 to 2. I think I want to rewrite that. Negative 5 to 2. So why did I use a bracket? Why did I squiggle that out? Well, at negative 5, right, at that value, that function is negative. But I think I want to go back and change that now. Now that I just wrote that, I think I'm going to change it to negative 5 and 2. Because now that I look at it, my first thought was at negative 5, it's below the x-axis. So bracket, right? But at negative 5, it's an open circle. So I'm not actually including that point. So once I saw that, now I'm going to change it back to a parentheses because I don't want to include negative 5. Even though that function is below the x-axis, I'm not including negative 5. But between negative 5 all the way up to 2, it's all below the x-axis. Number 9, sketch a graph given the following key features. So now you're kind of going in reverse. So instead of looking at a graph and coming up with the information, now you're given the information, you're going to sketch a graph. So you're just kind of going backwards. So they want a domain that runs from negative 5 to 5. So it would basically take up this whole graph. It's decreasing between negative 3 and 1. The x-intercepts are negative 4, negative 2. And then it's positive, which means it's above the y-axis from negative 4 to negative 2. So what I did, instead of me taking time to sketch this all out, I'm just going to show you what that should look like. So this is from your solutions manual, right? That you can access and look at it. Obviously, my paper is running out of my printer is running out of red ink, so I will re-sketch this. The domain is from negative 5 to 5, so you want to run all the way from negative 5 all the way over to positive 5. You don't want to include those points because they're parentheses, right? If you wanted to include them, they'd be brackets, so they're going to be open circles at that point. From negative 5 to 5. It's decreasing from negative 3 to 1. So from negative 3 all the way up to 1. So in that interval right there between those two values, it should be decreasing. X-intercepts are negative 4, negative 2. So that means it should be crossing at negative 4 and negative 2. So that tells me that that's got to be a piece right there. And then it's positive from negative 4 to negative 2. So it's got to be above the y-axis between negative 4 and negative 2. So something like that. Is that the only function? It doesn't say that the y-intercept has to be negative 2, right? It's saying that it's got to be positive between those two. It's got to be that wide. Could your sketch look differently? Yeah, it definitely could. It could look a little bit different than mine, but overall, it has to have those general characteristics. So number 10, communicate precisely. Jeffrey is emptying a 50-foot cubed container filled with water at a rate of half of a cubic foot per minute. Find and interpret the key features of this function. So my first idea is that I think they gave us enough information to kind of come up with an equation. So if this 50 cubic foot container is filled with water and it loses water at a rate of a half a cubic foot per minute, I think my equation is going to be 1/2 x equals 50. Looking at that, let me just verify it. Emptying rate. So 1/2 x. Ooh, no, I'm going to change that. So if it's already filled, so I'm going to switch this around a little bit. So ignore that. It's already filled with 50 cubic feet. I'm going to lose 1/2 per minute. There we go. That's what I want to have. It's basically the same equation. If I just subtracted 1/2 x over to the other side, it would be the same. But I want to set it up like this because I think that's going to help us visualize what's happening. So we have 50 cubic feet of water in a tank. We're losing, that's why I wanted to rewrite it like this. We're losing 1/2 cubic foot per minute, right? And then after we do that, we're going to end up with 0 water in the tank. So find and interpret the key features of this situation. So I think essentially what they're looking for is kind of what they were asking in 7 and 8. If I were to graph something like this, and you can do this as well, 50 would be my y-intercept. I wouldn't have anything to the left of x equals 0, like this is -1, -2, right? Because I can't have -1 minutes, -2 minutes, right? I would just start at 0. It would start at the y-intercept. And then I'm losing 1/2 per minute, 1/2 gallon per minute, or 1/2 cubic foot per minute. So this would be going down, and then it would end up at, I think just because the math is pretty easy, I can do this in my head. If you have 50 cubic feet in a truck or in a water tank and you lose 1/2 per minute, I think it's going to take 100 minutes for it to be empty. So it starts off at time 0 full at 50 cubic feet, but then after 100 minutes, it's down to empty. Okay, so that's just a quick sketch. That's not super accurate or anything, but it just gives you a visual representation of what it's talking about. So domain. I think our domain with this problem, make sure I'm on the paper. Domain, it runs from 0 all the way up to 100 because at time 0, I've got 50. After 100 minutes, I'd have 0 water. I wouldn't have any water left. So it's not going to exist outside of that. So domain would be from 0 to 100. My range, that's the height of the function. Looks like it runs from 0 to 50 because that's all the water it has in it. It either has 0 gallons or all the way up to and including 50. So the range would be 0 to 50. It's not increasing at all, right? This function is never going uphill. So it's only going downhill. So for an increasing function, there is none, right? It doesn't increase. I think I'm going off my paper here. Here we go. I'll just cover up that. What about decreasing though? It is decreasing, definitely. It's going downhill between 0 and 100. So from 0 to 100, it's going downhill. Why don't I include it at those points? Because at 0, it's not decreasing. I have to pass 0 for it to be going downhill. At 100, it's not decreasing. It's stagnant. It stays flat. So you always want to use parentheses when you're talking about increasing or decreasing. X-intercepts, trying to think of what else we have. Y-intercepts. My x-intercept is 100, so x equals 100. Or again, you could write 100 comma 0, same thing. Y-intercept is 50, so that's going to be y equals 50, or you could say 0 comma 50. I think that's it, right? Let me make sure I'm not missing positive zeros, x-intercepts. Yeah, I think that's it. All right, let's take a look at lesson 2. So lesson 2, there are different types of transformations that change the graph from the parent function. So remember, a parent function is just a basic function. So for example, something like y equals x squared, that's the parent function because I'm not adding, subtracting, multiplying, dividing. I'm not doing anything to it. So here is a child function, x squared minus 3, right? Y equals x plus 2 squared plus 4, right? Those are child function. A parent function is before you do any of this adding or subtracting or multiplying or anything to it, okay? A translation shifts each point on the graph the same distance and direction. So a translation is just shifting things around the page left and right, up and down. A reflection maps each point to a new point across a given line. So if you reflect across the x-axis, that means you're going to take that function and you're going to flip it across the x-axis. If you're reflecting across the y-axis, you're going to take the right side and you're going to flip it across the left side, and vice versa. The left flips across the right. A stretch or compress increases or decreasing the distance between the points of the graph and a given line by the same factor. So remember, there's stretching and compressing that's happening. I don't see an example here, but a stretch or compress would be something like this. Y equals 3x minus 2, right? That's a stretch of 3 because it's greater than 1. So things like that, if you don't remember that, make sure you go back to lesson 1, 2, go back to your notes, go back and review that information. You got to know what each of those different transformations are. So here's an example, graph the parent function, f of x equals absolute value of x. So the blue one is the parent function. You didn't do anything to it yet. And then this is the transformed function. The child function is what I typically call it. You'll notice that there's 3 transformations here. There's the first one that's inside the grouping symbols. Remember, you're always going in the opposite direction. So look at our vertex. Our vertex for the parent function is at 0, 0. So this is telling me x plus 2, but if I go in the opposite direction, that means I'm going to go left 2. So notice how it moved left 2. This is telling me to go up or down, so I'm going to go down 1. So notice that vertex moved left 2, down 1. But then that negative out in front, that tells you to reflect it across the x-axis, right? Flip it upside down. So instead of shifting it left 2 and down 1, then from that point there, it flipped it upside down. And that's exactly what this is talking about down here. So the descriptive part, multiplying by -1 is a reflection, adding 2, right? So read through that, make sure that you understand what those transformations were. Graph each function as a translation of its parent function. So what you're going to do is you're going to take this parent function, g of x equals absolute value of x, and you're just going to shift it down 7. So if you don't remember, this was our kind of our notes, I guess you could call it. So if you have a function like f of x equals, you'll have something like this: a parentheses x minus h squared plus k. So here's those transformations. If that a value is negative, it's going to reflect. If that a value is greater than 1, it's going to stretch it. If that a value is between 0 and 1, it's going to compress it. And again, if you're not sure what I'm talking about, what is stretch, what is compress, you got to go back to lesson 1, 2 and kind of review that stuff. This is just a quick reminder. Your h value, this moves you left or right, but remember, it's always in the opposite direction. Super key, you got to remember that. And the k value moves you up or down. Okay. There's also other transformations that they talked about in the lesson, but they never practiced, I don't believe, in any of the practice problems. And you have a b value here, technically. If we were in class, we wouldn't be learning that, but there's a b value that could be in front of x that would just affect your instead of reflecting you or stretching you or compressing you vertically, it would stretch you or compress you or reflect you horizontally. If we see that, we'll emphasize that here in a minute. So for something like this, g of x is the absolute value of x. So this is number 11. Let's see if I can get this on here. And just for the sake of time and ease, and to make it easier on me, I'm just going to use these graphs that are from that key in Canvas. So my absolute value of x, that's this blue function right here. That's the parent function. But that -7, that's your k value, so that's telling you to move down 7. So I took my vertex and I moved it down 7, and then just resketched my lines. Bam, bam. So that's what it would look like. Number 12, so my parent function is g of x equals x squared, and very similarly to number 11, this is just telling you to take that parabola and move it up 5. So for number 12, take a look at my graph. The blue function is just f of x or g of x equals x squared. I want to take that vertex at 0, 0 and move it up 5 places. So there's my new vertex, and then my function doesn't change. I just trace it back out. Graph the function g as a reflection of the graph of f across the given axis. So with number 13, you'll see number 13, that's the given absolute value of x. It looks like this function is probably something like f of x equals the absolute value of x, and then on the outside of the grouping symbols, it would say -2 because it shifted it right 2. The slope is still the same, up 1 over 1, so nothing else was different. So if they just want you to reflect it across the x-axis, what you're going to do is take that vertex, that's going to stay, and then just take all the points that were above the x-axis and flip them down. So for example, this next point right here, I went over 1, up 1. So now I just have to go over 1, down 1. This point right here, I had to go over 2, up 2. So now I want to go over 2, down 2. So you can see how it just reflects that and flips it upside down. And then this really jacked up function, I have no clue what that is, right? That's piecewise function. So I want to flip it across the y-axis. So essentially what I want to do, instead of like with number 13, where I take the top half and flip it down from the vertex, here I want to flip this across the y-axis. So what you see here, and I'm going to kind of trace this back out so you could see it. So there is my blue is my original function, and you could see that all I did was I took that right side, whatever was to the right side of my y-axis, and I flipped it to the left, and then I took the left side and I flipped it to the right. So I just reflected it across the y-axis. You can get points, and that's what I would recommend you do. This isn't going to change because that's on the y-axis. But you'll notice this next point right here, that went down 1, 2, 3 over 1, 2, 3. So I would still go down 1, 2, 3, but now I would go left 1, 2, 3. So you could see how you could build your function, right? This x-intercept right here was down 1 over 1. So the new x-intercept is going to be down 1, left 1. Okay, that's how you can build that function. 15, look for relationships. Describe the effect of a vertical stretch by a factor greater than 1 on the graph of the absolute value function. So a vertical stretch is basically going to take your graph, and if it's something like this, like an absolute value function, a vertical stretch is going to stretch all those y values and make them taller and taller and taller. So something like this, if I had like a parabola, if I stretch that parabola, it would look something like this. They would just get stretched out. Almost from, you'd grab the bottom and the top of the parabola and stretch it. It would become thinner and thinner and thinner. How is it different from the effect of a horizontal stretch by the same factor? It's basically the opposite. So if you are stretching or compressing horizontally, you're going to be doing the opposite effect. So if I have a function like this, y equals 2x squared, right? That is vertical stretch. So the parabola would become more and more narrow. If I had something like this, y equals 2x squared, it would become more and more, it would become flatter. So something like that, right? It kind of has the opposite effect on it, horizontal versus vertical stretch or compress. Use structure, graph the function that is a vertical stretch by a factor of 3.5 from the parent function f of x equals absolute value of x. So this is 16. So you'll notice for number 16, the blue function is my absolute value function. No stretch or compress, nothing's applied to it. It's just the basic parent function. But now they want me to stretch it vertically by a factor of 3.5. So it would look something like this if I were to write this out. Y equals 3.5x. So that would be my function. Y equals 3.5 times the absolute value of x. So what essentially is happening is I'm taking every y value and multiplying it by 3.5. So for example, let's take a look at this point. If I go over 2, up 2, there's my point on my parent graph. But now what's happening is I'm going to take all my y values and multiply it by 3.5. So instead of going over 2, up 2, I'm going to go over 2, up 7. So over 2, up 7, right? Because I'm multiplying that y value, that height, I'm multiplying it by 3.5. So that's what's happening when you're vertically stretching something. Graph the function that is a horizontal translation 1 unit to the right of the parent function, f of x equals x squared. So you could see with number 17, my blue function is my parent function. Nothing's happened to that. But if you want to shift it to the right one, that means every point on this graph, I typically talk about the vertex shifted right 1. Every single point shifted 1. Notice right here at 1, 1, that shifted over to 2, 1. Everything shifts right 1. And that function would look like this. Y equals x squared. If we want it to go right 1, I'm going to have to erase that. Y equals, if I want everything to shift right 1, it would be x minus 1 squared. Remember, you always go in the opposite direction. Lesson 1.3. Moving along. Piecewise defined functions. So a piecewise defined function is a function defined by 2 or more function rules. So that's what they're calling these things. These things right here in number 18, those are all rules over different intervals. A step function pairs every number in an interval with a single value. So I don't see any step functions, but you can go back to lesson 1.3 and see an example of that. The graph of a step function can look like steps of a staircase, which is exactly where they get that name from, a step function. It literally just looks like a bunch of flat vertical or flat horizontal lines that are stepping up. So they want you to graph this function. They want you to graph y equals -3, y equals x plus 1, y equals -x plus 2. So essentially what you're doing here, and you could see how they all match up. -3 is black, that matches to the black graph. X plus 1 is red, that's the red. -x plus 2 is blue, that's the blue. What you're essentially doing is taking this piecewise function, you're graphing all 3 functions onto one graph, but here's the caveat. You're only keeping this part of the domain, right? These are all domain values. You know that because they're all x's. If they said y, that would be the range. So you're only keeping y equals -3. Technically, that's a flat line that goes on forever. but you're only keeping the piece from -5 up to, but not including -2. So at -5, it's less than or equal to, so it's a solid circle. At -2, it's strictly less than, so it's an open circle, and I'm only keeping that piece between those two values. Same thing with x plus 1. That's a line that goes on forever, right? Down and to the left, up and to the right. But I'm only keeping the piece of that function that's between -2 and 2. Since they're both less thans, I only want to use open circles. I don't want to use a closed circle. I don't want to include those two values. I just want to keep the piece between -2 and 2. So at -2, that's where it begins. And you could see at 2, that's where it ends. So I only keep the piece between -2 and 2. And then same thing with our blue function. So graph that function. What's its domain? What's its range? Increasing, constant, decreasing, right? That's everything that we've talked about so far, I think, in lesson 1.1. So graph each function. This is an example of a step function right here. So you'll notice that it's always y equals a number, y equals a number, y equals a number, y equals a number. Okay, so this is a step function. Let me see if I can get my graph. Number 18. So for number 18, you want to graph y equals 3. Anytime you graph a line like y equals a constant, it's always going to be a flat line. Okay? But you want to graph y equals -3. So on your y-axis, look where -3 is at. Looks like it's right there. But you only want to keep the piece that's between and including -4 all the way up to, but not including -2. Right? I want to include -4 because it's less than or equal to. So at -4, I want to make a closed circle. And then at -2, I want to make an open circle because it's strictly less than. So what I would do if this was me making this on a graph, I would sketch that line, y equals -3. So it would look something like, I would sketch this line, y equals -3, just like that. I wouldn't draw it super hard on the paper because I want to be able to erase it. And then I would look, okay, it only wants to exist between -4 and -2. So outside of -4 to the left, I want to erase it. Outside of -2 to the right, I want to erase it. And I'm only going to keep that piece. So at -4, it's less than or equal to, so it's going to be a solid circle. At -2, it's less than, so it's going to be an open circle. Some people can draw each piece at a time. To me, it's just easier to draw the entire line and graph it and then erase what I don't need. So it's up to you though. So same steps with y equals -1, y equals 1, y equals 3. Just make sure you're watching those signs. Less than or equal to means it's a closed circle. Less than means it's an open circle. And you should never have two steps overlapping. So notice like right here, when x equals 2. Right? Notice one is closed and one is open. You could never have two closed circles there. It wouldn't be a function if you did. You can't have two different y values for one single x value. If you want to have two open circles, you could definitely do that. It could skip that x value altogether, but it couldn't be two closed circles. Number 19, so this is just a regular piecewise function. You want to graph y equals 2x plus 5, y equals -x minus 2, y equals x minus 3. And that's exactly what I do. It looks like my paper is, or my ink really ran out with number 19. So I'm just going to go ahead and graph these for you on the paper. So y equals 2x plus 5. So if you forgot how to graph a line, that might be something to go back and review, something that's going to be super beneficial. My y-intercept, that's the first thing I want to graph. So +5. I don't know why I'm using a pen because I'm not going to be able to erase that. +5. And then my slope is 2x. So it's going to go up 2 over 1, up 2 over 1. But obviously I can't keep going up 2, right? I'm off the page. So going up 2 over 1 is the same thing as going down 2 left 1, down 2 left 1, down 2 left 1. So there is my graph. for that line, and I only want to keep that line if x is less than -3. So this is my line, x equals -3, so I'm going to erase all this junk up here. And then they specifically want less than, so I'm going to have an open circle at that point. So there's my first piece. Y equals -x minus 2. I know it's going to be a downhill slope because it's a negative slope. So -2 is my first y-intercept. That's my first point. My slope is -1, so it's going to go down 1 over 1, down 1 over 1, down 1 over 1. Remember, down and right is the same thing as up and left. So I can go up and left, up and left. So this is my function right here. And I only want to keep that function between -3 and 1. So outside of -3, I don't want it. So I'm going to erase it. Outside of 1, I don't want it. So I'm going to erase it. At -3, it's less than or equal to. So that's going to be a solid circle at that point. And then at 1, it's strictly less than, so it's going to be an open circle. And then our last one, x minus 3. So -3 is my y-intercept. My slope is +1, so it's going to go up 1 over 1, up 1 over 1. So it's going to look something like that. But I only want to keep that graph when x is greater than or equal to 1. So only when it's greater than or equal to 1. So I want to erase basically all that, which is messing with my other line. Okay. Since it's greater than or equal to 1, that means it's going to be a solid circle at that point. And then I would just indicate that it goes on forever. Same thing with over here. I should indicate that it goes on forever. So for number 19, that would be a piecewise function graphed. Again, that's the way I would do it. I would graph the entire line, just erase the parts that you don't need or that you don't want. What rule defines the function? So a rule, again, look at number 18 and 19. That's the rule for those functions. So they basically want you to take the picture and then write the rule. So go backwards. So for number 20, my desk is crazy messy right now. So for number 20, what rule defines the function of the following graph? So we'll just say y. So this is number 20. We'll call this y. Start with this one over here. It looks like my slope, if I go up and over, it's not hitting any lines. It's not hitting. There's my first line right there. So if you zoom in and you look at the grid lines in the background, this function right here, that's one point at -3, -3. And then this is the second point at -5, 0. So that'll tell me the slope, up 1, 2, 3 over 2. So in this case, my slope is -3/2, right? It's going downhill from left to right, so I know it's negative. And then again, let's find the y-intercept. If I go down 3, 1, 2, 3 over 2, I'm not to the y-axis yet. But if I go down, it looks like I'm going to have to go over 1. So it's going to be down 1.5 over 1, right? Down 3 over 2 is the same thing as going down 1.5 over 1. So down 1.5, that's a -6, so -7.5. So they're throwing some fractions out at you. So that is the function for that graph right there. But you only want to keep the part when x is less than -3. So you only want to keep the part when x is less than -3. How do I know less than? Well, again, it's an open circle, so it's strictly less than. The second part looks like from here to there, right? Looks like my slope is up 1 over 1, 2, 3, 4, 5. So my slope is going to be 1/5. If you don't remember how to create an equation based off of a graph, that would be something to kind of research, watch a video on. That's kind of, pre-algebra, algebra stuff. I'm happy to help you out if you do need some help with that. Let me know. But all you're doing is finding the two pieces to the equation, the slope and the y-intercept. It's looking like the y-intercept might be like 1.5, but we need to be sure. So what we're going to do is we're going to go up. Well, it's not going to be 1.5. It's going to be a little bit higher than that. So 1/5 x. If I go up 1/5 for my slope, that means it's going to go up 1/5 each time. So if I keep going up 1/5 for each of those sections, assuming I'm starting here at 1, I think I'm going to end up at 8/5, right? So this is a lot of fractions at you, but y equals 1, that's the same thing as 5/5, right? If my slope is 1/5 and I start at 5/5, because that's where I'm at right here at the beginning, I'm going to go up 1/5 every time I go over 1. So over 1, over 1, over 1. I went over 3 times. That means I should go up 3/5 from 5/5. So that's going to be 8/5. I know that is like blowing people's minds right now. But again, go out and watch a video. If you forgot how to create a line or create an equation from a line, just Google that, how to create an equation from a line, from a graph line. It looks like this exists between -3 and 2. So I'm going to say -3. They're both solid circles. And then our last equation looks like a flat line. So y equals 3. That's pretty straightforward. It's an open circle at 2 and a closed circle at 5. So it runs from 2 all the way up to and including 5. If you need some clarification about, creating these equations, again, contact me, let me know. I'd be happy to explain that further to you. But we'll leave it at that since this is just a review. 21, can every transformation of the absolute value function also be written as a piecewise defined function? So if they give you an absolute value function, can you write that as a piecewise function? Yeah, I would think so. The graph of every absolute value function has two pieces, right? If I have something like this, I'm just going to make something up. Something like this, right? There's basically two pieces here. There's this piece right there, the increasing part, the part that's going uphill, and then the part that's going downhill. So for any absolute value function, you could split that right across that vertex. And you could talk about this piece that's going downhill and then talk about this piece that's going uphill. So I would say, yeah. 22, a coach is trying to decide how many new uniforms to purchase for a softball team. If the coach orders more than 10 uniforms, the cost for the extra uniforms is 0.75 times the normal cost per uniform of $120. Write a piecewise defined function that gives you the cost C in dollars in terms of the number of uniforms N the coach purchases. Determine how much the coach will pay for 18 uniforms. Ooh. All right, so I'm going to call this... You can call it Y. You can call it whatever you want. Do they tell you actually to call it? They're saying C of N. So I think we do have to call it C of N. Technically, we have to call it C of N. So I'll do it. I'll do what I'm told. So the first equation, the first part of this piecewise function, I think is dealing with the $120 that they were talking about. So they said... the normal cost of a uniform is $120, but you basically get this discount once you purchase more. So I think that's the two pieces they're looking for here. The normal cost, so if that's $120, that's going to be $120 per uniform, right? And then you only get that discount, if I remember correctly, if you order more than 10 or at least 10. Let me check. Purchase if the coach purchases more than 10 uniforms. So you're going to pay this base price if you purchase 10 uniforms. So in this case, it's going to be from 0 all the way up to and including 10. You only get that discount if you order more than 10. Now is where the discount comes into play when you're ordering more than 10 uniforms. Let's go back and reread this. So 0.75 times the normal cost. So if I'm paying $120 per uniform, 3/4 of that price is just $90, right? 0.75 times 120 is 90. So I think that's what I'll be paying per uniform after 10 uniforms is $90, right? $90. But the thing you have to remember is if you're ordering, let's say it over here, if you're ordering more than 10 uniforms, that means you've already purchased 10 of these base price uniforms. So the only time I get this discount if I've already ordered 10 of those $120 uniforms. So I've got to include that here. So if I ordered 10 of them, that would be $1,200. So what this is telling you is if you order from 0, technically this should be, because you're not going to pay anything, right? You're not going to order 0 uniforms and pay money. So from 0 all the way up to including 10, you're paying $120 per uniform. But once you order more than 10 uniforms, now you're paying $90 per uniform, but you've already ordered the 10 uniforms from before it. So you've got to include that value in your price. All right. Did they ask you anything else? Determine how much the coach will pay for 18 uniforms. So for 18 uniforms, I could just use this second equation right here. 90 times 18 plus 1,200. 90 times 10, that's 900. 1,800. I'm just doing this in my head. 1,680. Oh, no. 720. 720 plus 1,200. That's going to be, so for 18 uniforms, I think it's going to be $1,920. If I'm screwing that up, I'm sorry. But all I'm doing is plugging that in here. So 90 times 18 plus 1,200. Hopefully that equals that. All right. Woo! 1-4, we're skipping. Sequences and series suck. We always skip them every year, so I'm glad they skipped them this year. I think what I'm going to do is I'm going to take a break, and then I'm going to go ahead and do lessons 5 and 6 here in just a few minutes. That way this comes in under an hour. We're going to skip lesson 7. So I will come back and see you in lessons 5 and 6.